Hi, everyone. We are on our last slide deck for the semester, which is very exciting. I'm sure you all have had such a wonderful time that this has just flown by and been a general delight. What we're going to finish with, if you choked on your coffee or whatever happened after I said you had a delightful time, once you've recovered, what we're going to talk about in this last slide deck over the course of a few videos is test bias. When we talked about validity in some of the previous videos, we talked about bias, and even when we talked about reliability, we talked about bias as a systematic bias where different groups get different scores, not because necessarily they differ on their true score, but because they might differ for some other reason. We're not concerned about, in this case, the reason so much as how can we detect bias? And this is really critical because we want to show, hopefully, that measures we use don't have bias, or that different groups don't respond differently or have different outcomes based on their group membership. We want to be able to show that men and women respond in the same way. Ideally, we're showing that, but it's important to know how to detect bias regardless, so that you can at least identify how much bias you might have and if that's going to be a problem. So what we'll walk through in this slide deck is really kind of some terminology things about how we talk about bias and how it manifests. And then we'll actually walk through some fairly practical ways to detect bias. So it's not like validity when we say, okay, these are overarching concepts you should think of. Test bias is something that statistically we can dig into to see if it exists or not. And there are a number of different approaches that sort of vary in their sophistication level that we can talk about. So we use the term test bias because that's what everyone understands. But I want to make the point that differences between groups, say differences between men and women, differences between grad students and undergrads on tests, doesn't mean that there's bias. It could represent a true difference between these two groups. So to use the previous example, let's say I gave a psychometrics test to you all, and I gave a psychometrics test to a group of second-year psychology undergraduate students. I would very much hope that there would be a difference between those. Is that bias? No. You have different true scores on that, so you get group differences. So group differences alone doesn't mean there's bias. What you really need to do is compare two people that have the same true score or ability level, if you want to talk in IRT terms, and see if they respond differently to items. A good way the GRE does this. They do this in a IRT manner, in a very sophisticated manner, but they figure out what your ability level is. If you think back to IRT, what your theta level is, and then they give you items in that sort of experimental condition to see if people respond similarly or differently if they have the same true score. We'll talk about that later. But I want to make the point that bias is an interpretation of group differences. Group differences exist in different forms, you all versus the undergrads. The interpretation of whether or not that bias is biased is variable, it's dependent, right? And in this case, I would say probably, yeah, that test isn't really biased against undergrads in particular. It just means that you all know more about it. So what we're going to try to do is avoid the term bias here because that's the interpretation, and today focus primarily on identifying group differences and figuring out if they're problematic or not. We're going to look into the statistics of it. And that line is going to be blurred because it's hard to avoid adding an interpretation on, but hopefully at least this point here makes you think about or drives home the point that group differences don't mean there's bias. Bias could be a result of group differences, but it is not always. So we want to think critically about that. And when we do so, we kind of come to this point of, is it possible for a test to be biased but fair? Or conversely, is it possible for a test to be biased but unfair? And my answer to both of these would be a resounding yes. Yes, it absolutely is. Bias is the interpretation, but it's also the psychometric term we use when we have these differences. Fairness is a sociopolitical issue. What is fair, for example, in the United States, may not be fair somewhere else, or might be extremely fair somewhere else. Fairness has these cultural connotations to it. People, even within the United States, view different things as fair or not. I mean, if you honestly flip on the news, and that's a euphemism these days, if you go to whatever your favorite media site is and read some articles, and God forbid if you read the comments, you'll realize that fairness is a social construct. That's a sociological issue. We are concerned with psychometric issues. We're concerned with bias as a technical term that is a potential consequence of group differences. So just a quick note, be careful how you use those. The average person on the street won't understand those, but if you get in a technical discussion in your future employment, you want to make sure you're using these terms correctly. So when we talk about bias, we want to know, does this item show construct bias? And the conditions for construct bias are people belonging differently to different groups, graduate students and undergraduates, respond differently to an item, and this is critical, and that those responses weren't related to existing group differences. The typical graduate student is older than the typical undergraduate student. So we need to show that these responses are different, not because there are fundamental differences between grad students and undergrads, that there's group differences because you all have had more classes, but they're due to something else. So the problem with this is we need to know if there are actual group differences on what you're trying to measure. This kind of gets a little chicken and the egg, right? You need to see if people are responding for reasons other than their ability, but first you have to figure out their ability. We can do that, and we'll talk about different ways to do that, though. That's the IRT piece. So ideally, to detect bias, to show that we have construct bias, we want to compare respondents from both groups, know that they have the same level of the attribute, and see if they respond differently. Another way to think about this is not necessarily with pitchers of water, but we have bias if the item taps or gets at a different construct for each group. We talk about this idea of stereotype threat in social psychology, right? And there's mixed, they have problems replicating that too, but let's go with it. Where one group gets a test and they answer the test based on what they know. The other group is primed, or some stereotype about their cognitive ability is made salient. So they're not thinking about the problem entirely. They're thinking about that stereotype. We'll walk into the male and female example here in a moment, but another example to kind of get this in your heads is a colleague and I are studying stereotypes of older workers and the effect on pre-employment hiring tests. If you look for a job, how are you going to perform when they have you take a cognitive ability test or a memory test or things like that? And our thought is that there are stereotypes of older people not being as quick on their feet cognitively and not having as great a memory. So we're wondering, do younger people just answer the questions? And do older people not do as well, not because cognitively they're worse off, but because they're thinking of this stereotype and handicapping themselves? There's evidence for this effect for men and women in STEM, in the sciences. And there's lots of good work being done, probably not enough, on reducing this and teaching women that from an early age that this stereotype isn't true. But if it is, and you look at this pitcher of water and you ask a group of men, you ask a group of women, which pitcher of water will stay cold longer? For men, you're just measuring thermodynamic knowledge, which is the knowledge of heat transfer, I think. And in this case, this is our regression equation, and we're going to circle back to regression in a second, but our single predictor is knowledge, right? We have our outcome, our intercept, our error, and then our B weight, which is how much thermodynamic knowledge do we have? The more knowledge you have, the more you would be expected to get this right. For women, you're not just measuring the construct of thermodynamic knowledge. You have another predictor in there. And that predictor is stereotype threat. So now the things that go into answering this question aren't just how much you know about thermodynamics, but it's how much you know about that stereotype and how much it affects you. In this case, we would then conclude there is bias because these items are tapping fundamentally different constructs for these two groups. By the way, I think that they stay cold the same amount of time, but I'm not sure because I don't know anything about thermodynamics. And to be perfectly honest, this comes up every year. I look it up after class and then I immediately forget the right answer because my brain doesn't need this information. So I think it just shuttles it off somewhere else. Okay. We're going to spend the rest of this set of slides talking about how we detect bias. And there are two big umbrellas of ways that we can do this. We can do internal methods and external methods. We're going to start off with the external methods and talk about two subtypes of that, predictive bias and outcome bias. In the next video, we'll talk about the internal methods. So today, external methods, and we start with predictive bias. Basically, does a test predict an outcome equally well for different groups? If we are trying to predict performance in graduate school, does the GRE predict equally well for different groups? This is basically a generalizability question, right? Do the results, when we give the GRE to everyone and look at how it predicts graduate performance, can we generalize that to different groups? And one key thing to note, and we'll walk through regression here in just one second, but one key thing to note is there's a couple different moving pieces here. We have our predictor, the GRE, and our outcome, graduate student success. Let's just say it's graduate school GPA, just to oversimplify for the sake of example. Typically, we focus on bias in the predictor, bias in the GRE in this case, but the outcome could possibly be biased. And just like that, I said with generalizability, we're essentially comparing the scores for different groups against our overall one-size-fits-all. So we have an overall relationship between the GRE and GPA for everyone. We will compare whatever groups we want against that to see if they're similar. And the way that we do that is through regression. We compare regression equations. And we talked about this now quite some time ago, so I just want to remind you what regression allows us to use one or more predictors to predict an outcome. And we can figure out how well we predict that. How good is our prediction? What is our R squared? How much variance are we explaining in our outcome? So the key terms that I want you all to keep in mind today are that we have an intercept and a slope. An intercept is the value of y when x equals 0, and the slope is basically the degree to which your predictor matters. A larger slope means that your predictor is more explanatory. A smaller slope means that your predictor is less explanatory. So don't worry too much about the equation, but what we will be doing for this particular approach is comparing intercepts and slopes from our one-size-fits-all to our different subgroups. So the first step is we calculate a regression equation for everyone. Everyone that takes the GRE get that regression equation. Then let's say that we're concerned about differences between men and women. And I'm picking that example solely because it's two groups, so it makes for a cleaner example. We'd calculate a regression equation for men using the GRE as a predictor and GPA as an outcome, and a regression equation for women using those same predictors and outcomes. So now we have three different equations. We have one, our overall, two, regression equation for men, and three, regression equation for women. Now, to see if there's evidence for bias, what we'll do is we'll compare men to the overall and women to the overall. But how do we compare them? Do we just write them all out next to each other and say, these numbers are different, that's probably not good? No, we fortunately have more sophisticated ways to do this. We can look at what's called peer intercept bias. We can see, are the slopes the same or different? Remember, the slope is where x equals 0, what the value of y is, so it's the y-intercept. Is the y-intercept different? Here we have men, the overall, and women. Here's, if you can see my cursor, the intercept for, technically it extends down here, for women, for overall, and for men. Is this biased? Well, if you have intercept bias, and if you just look at these scores, you'd think that individuals from two groups that are equal in aptitude will get consistently different scores. In this case, males do consistently worse on the outcome than the overall, and women do better. Is this biased, though? It could be that there's differences here. There's genuine important differences here, that women do better on the outcome tests than men with the same aptitude score. Pure intercept bias by itself doesn't necessarily mean that there is bias, although if you look at this graph, you would think that's maybe not great. What we tend to want to do is get a little bit more sophisticated. So this is a building block. We look at pure intercept bias first to see, are there differences in where, I'll go back to make this a little bigger, in where the lines hit the y-axis or the outcome axis. Here, males have a lower outcome, common has a higher, and females have even higher. And remember, we're comparing females to common, males to common. What gets more interesting and more indicative of having an actual problem is what we call pure slope bias, where the intercepts are about the same, but the slope is different. The relationship between your GRE scores and your GPA for women is really strong here. It's moderately strong for the overall, and it's not very strong for men. That can be a pretty big problem. It's now showing that there's not differences in just how well people do, there's differences in how much our predictor affects our outcome. There's differences in how much the GRE relates to GPA between these two gender groups. So pure slope bias, less good. Definitely should raise some eyebrows. These examples rarely happen in real life. Those are nice, clean ones. You're oftentimes going to get something like this, where you have, and I know it might be hard to see, you have intercept bias here on the left when everything intersects with the y-axis, and you have very clear differences in slope. So how do we know if we have a problem? I'm not going to walk through it today because it's technically like a whole different stats topic, but we can do tested moderation and see if the interaction between slope and intercept is significant to see if we have bias. I'm going to go through a really handy table in a few seconds here or maybe a minute, to walk through what is a problem and what isn't, though. Because right now, some of this stuff was developed by a guy named Cleary. He didn't do a great job saying, here's what we should and shouldn't be worried about. So we'll give you more guidance to that in just a moment. One thing to keep in mind that just makes this more confusing is that there's other reasons why a test may be biased, other than bias right now we're talking about bias in the predictor. The GRE is biased. It could be that GPA is biased, that women or men consistently get higher grades because of their gender. It could be unreliability. If the GRE or GPA is unreliable, we're not going to get very stable estimates, and we're going to have problems. Or we could have omitted or third variables in here causing havoc that we aren't capturing. So just because we have slope or intercept differences doesn't, or especially intercept differences, doesn't mean there's bias, just that there could be. You want to flag it. So this is probably the easiest way to see if you have bias. Just calculate regressions. You guys can probably think about how to do this in your heads in SPSS. You know, split file by output, split it on gender, get the common one as well, run a regression. It's like what we did with means a while back, just a little using a different test. So the problem with the method as this was originally put out was that it just said that there could be test bias. It looked at the regression lines and said, both of these things indicate that you could have a problem. And that's not very satisfactory. It doesn't give us guidance on determining, do we have a problem or not? So Mead and Fetzer in 2009, I think in an ORM article, came out with a revised method that looks at group differences in slope, intercept, predictor, and criterion. And they say, if there's slope bias, then you have a problem. If there's just intercept bias, that's not enough evidence to say you definitely have a problem. And if the intercept and predictor tests are different, don't use. The intercept test is different intercepts between groups. The predictor test we haven't talked about before, but this is just looking at different means between groups. So what Mead and Fetzer say is, if there's slope bias, don't use it. Or if there's intercept bias and intercept bias alone, that's fine. But if you have intercept bias and different means between your groups, so men and women have different means in their outcomes, or in their predictors rather, if you combine those, you don't want to use them either. So this gives us some more guidance. Slope bias, bad. Intercept and predictor, bad. And they helpfully clarify this in this table. Intercept test is intercept bias. Are there differences in the intercept? Predictor test is, are there differences in the means of the predictor, the means of the GRE in this case? And criterion tests are there group differences in performance or GPA, whatever our outcome is. And this outlines different scenarios when you might or might not want to use this test or determine if you have bias. And honestly, I use this table whenever stuff like this comes up. I immediately go to this table and kind of walk through their sort of decision tree here, and I find it very helpful. So that, folks, is our introduction to test bias. What we'll end with next time is outcome bias. Right now we talked about predictor bias, basically. We're going to talk about outcome bias, and then actually we can talk about outcome bias. So this is all external methods, right? External methods of detecting bias, internal and external. I'm sorry. External methods are predictor and outcome bias. Outcome bias is just saying that you want to look at your DV as well. Your dependent variable or outcome may be biased too. So you can do the same sort of things and just switch it around. What do I mean by that? Right now in our example, we're using GPA or GRE to predict GPA. We could easily switch that. Just in our regression, switch it and run the same tests. And it's worthwhile to do that as well to make sure what you're choosing as your outcome variable is also unbiased. Sorry, that I realized, yeah, we should hit that at the end today. The next video will cover internal tests of bias. So our external tests, predictor and outcome tests, all rely on regression. And these were hopefully at least intuitive, or they made sense to you. Even if you aren't confident in sitting down and doing them right away, hopefully you're like, okay, I get the logic. In our next video, we will talk about internal tests of bias. Sorry, I just lost my train of thought. And to do so, we're going to go back, not hard, super hard, but into our idea of item response theory and our idea of item difficulty and discrimination and item functioning as a more sophisticated way to detect bias in our results. But that's it for today, folks. For this video, stay tuned for the next one.